Hi, so we continue with the operation amplifiers and the filters in particular. Let's try to obtain the response of this circuit as shown here. So as before, input signal is Vi, output signal is Vo. We have a parallel combination of resistor and capacitor in the feedback, and we have the series combination here in the input side. So let's define the gain of op amp to be A, the current flowing through the network, call it as I1. And because of the op amp's infinite input impedance, ideally, we say that no current can pass through the input terminals of op amp. So the same current I1 flows through this feedback network. Let's call it as a I2. And this combination, as said before, is called as feedback network. Let's define it as a Z2 of S, which is impedance 2. And this combination right over here, let's define it as Z1 of S, which is the input side impedance. And as before, we see that V2 is equal to V1, where V2 is the node voltage at this terminal, and at this terminal, the node voltage is V1, and that is equal to 0 because we assume the gain is ideally infinity. So this is a virtual short concept. And because of that, we have this configuration where current I1 is equal to I2. So of course, I1 would be Vi minus 0 divided by Z1 of S, and I2 would be 0 minus Vo divided by Z2 of S. And this simplifies to Vi of S. We call them as S Vi minus 0. So it will be Z1 of S minus Vo of S, Z2 of S. And we try to solve them. Minus Z2 of S divided by C1 of S. So that's how it looks like. What about Z1 and Z2? So we define them. Z1 of S is the series combination of this capacitor and the resistor. So it would be given as C1 of S, which can be simplified as R1 C1 S plus 1 divided by C1 of S. And Z2 of S is the parallel combination of capacitor and the resistor R2 and C2 respectively. So it would be R2 times S C2 of S 1 divided by C2 of S. This term gets cancelled. Final value for Z2 of S is 1 plus R2 C2 S. So that's how we get this configuration right over here. Once we have these two values, we come back to this expression right here and try to plug in those values in this expression. So what we see here, minus Z2 is now this. So it would be R2 divided by 1 plus R2 C2 of S divided by value of Z1 of S is right here. So 1 plus R1 C1 S divided by C1 of S. So we try to solve them. We write like this. R2 C2 of S into C1 of S 1 plus R1 C1 of S. Yeah. So we try to put S equal to G omega in the above equation, and therefore we get the new values right here. Let's uh, write it in the next page. So it would be given as VO of j omega, VI of j omega. This is the ratio of two voltages. And it takes the value of R2 divided by 1 plus j omega by omega C1, not C1, omega C2, divided by 1 plus j omega by omega C1 divided by j omega C1. So we define here omega C2 is 1 over R2 C2 and omega C1 is 1 over R1 C1. So that's how this configuration looks like. We arrange these terms in a proper format into j omega C1 divided by 1 plus j omega by omega C1. So we see here this configuration minus R2 C1 j times omega, and these two terms are like this 1 plus j omega by omega C2. So that's one term, and second term is this one omega by omega C1. This is second. So in the numerator, we have this 0, and in the denominator, we have two poles right here. How do we represent them in the S-plane? Like this is real part, this is the imaginary part right here. So in the numerator, we have 0 on the imaginary axis with the value of omega R2 C1. And in the denominator, we have the two poles, that is 1 plus j omega by omega C2. So somewhere here, we have this pole, which is omega R2 C2. And this is another pole again at omega R1 and C1. So we have these two poles here. Of course, with the values chosen for we'll say that let's say omega C2 and omega C1. So these two frequencies poles are there, and that's how they will make the phase angle right here. So we'll see that later what values, what frequencies they are placed. That depends on the values we choose for the resistors and the capacitor here. So what about now we try to obtain the magnitude of this plot. So VO of j, VI, j omega. So we focus on this equation here. So real part is 0. It would be square root of 0 square plus omega R2 C1 whole square divided by square root of this term, that is 1 square plus omega by omega C2 whole square. And again, we have a square root for 1 square plus omega by omega C1 whole square. Further simplifying it to, we get this value, square root of 1 plus omega over omega C2 whole square, and another value is 1 plus omega over omega C1 whole square. What about angle? Angle could be calculated as like this. The phase of the numerator is minus 90 degree because we have minus j there. So the phase right over here, that's the value of phase minus 90 degree. And minus of tan inverse of omega by omega C2. That is the value what we have here, plus tan inverse of omega over omega C1. So that's the expression for the phase right here. So once we obtain the values for magnitude and phase, we can get these exact values for certain frequencies. So the phase would be j omega would be j omega times R2C2. And so omega SR2C2. Yes. So SR2C2 0 minus 1. So S equal to minus 1 by R2C2. Minus 1 by R2C2 that is equal to minus 1 by J or equal to minus J plus J R2C2. R2C2. All right, so now we have the expression for magnitude and the phase angle. Let's get these values for the three cases. First case is at omega is equal to 0. The magnitude will take this form. We see that this is the expression. This is the expression that we are focusing upon. So omega is 0 here. So let's see what it value it takes. 0 divided by 1 plus 0 square, and this is 1 plus 0 square. So it's basically 0, right? Because we have omega 0 here, omega 0 here. And the phase would be phi would be minus 90 degree, minus of tan inverse of 0 plus tan inverse of 0. So it would be minus 90 degree. So we are focusing upon this equation right here. So omega is 0 here. So this is the case one. All right. What about at omega is equal to omega C1? So omega C1, remember, is 1 over R1 C1. So in that case, we write that the magnitude, now this has a value of indicated by A. So we put the value 1 over R1 C1 times R2 times C1 divided by square root of 1 plus the value of omega, now omega C1, and omega C2 is this one. So we write 1 over R1 C1 divided by 1 over R2 C2. So omega C2 is 1 over R2 times C2, okay? So can we write it in this way? R2 C2 by 1. And we see that this closes. And this another bracket. We have this one. This is omega over omega C1. So now 1 plus 1 by R1 C1 times R1 C1. This is how it goes. So these two terms get cancelled, and we have C1 gets cancelled in the numerator. So we have R2 over R1 divided by square root of 1 plus R2 C2 divided by R1 C1. If these two, if numerator and the denominator, they are same, then this term gets converted to 1 here. And right over here, what we have is 1 plus 1. All right. So this final value that we are trying to obtain is R2 over R1, and in the numerator, in the denominator, we have these two terms, 1 plus R2 C2 divided by R1 times C1. Okay. So if the ratio of R2 and R1 is equal to 1 and C2 over C1 is equal to 1, then this takes the value of root 2 times root 2. So that is R2 times R2 over R1 divided by 2. If the ratio of R2 and R1 and C2 of C1 that is equal to 1. Rather we write it in this fashion. Okay. C1 is equal to 1. Okay, and the angle in that case, minus 90 degree would be minus tan inverse. Now we have this equation right here. So omega is omega C1. So again, we have to write 1 by R1 C1, R2 times C2. That is our expression, plus tan inverse 1 by R1 C1 times R1 C1 here. Okay. So what we see here, this is minus 90 degree, minus of tan inverse of R2 C2 divided by R1 C1 plus tan inverse of 1, because these two terms get cancelled right here. And again, if the R2 over R1 equal to C2 over C1 is equal to 1, so this term right here is also tan inverse of 1. So finally, before that, we see that it is minus 90 degree minus of tan inverse R2 C2 R1 C1 plus tan inverse 1 is 45 degree right here. So is minus 90 minus 45, it is minus 135, minus 135 degree, minus of tan inverse R2C2 divided by R1C1, and this takes the value of tan inverse of 1 if R2 over R1 equal to C2 over C1, that is equals to 1. And then this is the final value of the phase would be minus 180 degree. So we can actually see and simulate this behavior if that's the case. So that's the case number 2. See that. Okay. What about the case number 3, where we have omega is equal to omega C2. Let's analyze that, how that goes. So in this situation, omega is equal to omega C2. I think what we derived here, we are going to have obtained the same expressions as before right here. So we can actually solve them. You can keep it to yourself. For instance, we have this expression of the gain, and we plug in the values of omega C2 in this case now. And we'll have the finite gain value, and accordingly we'll have the phase. So let's see what that value of phase is. So it would be, let's solve it, why not? 1 over R2C2 times R2 times C1 divided by square root of 1 plus omega C2 is 1 over R2C2 times, what's the value here? 1 by R2C2 into R2C2 into R times C2 by 1. And there's another term here. This is 1 plus 1 by R2C2 times R1C1. So we see here R2 gets cancelled. So instead of resistor ratio, we have a capacitor ratio now. And here we have these two terms getting cancelled. So it is 1 plus 1. And in this another bracket, we have this 1 plus R1 C1 R2 C2. So that finally simplifies to root 2 divided by into 1 plus R1 C1 R2 times C2. What about the phase? So it would be minus 90 degree minus tan inverse of 1 by R2 C2 times R2 C2 plus tan inverse of 1 by R2 C2 times R1 C1 right here. So that's the expression for the phase we have obtained here. So we put the value of omega C2 first and then omega C2 here. Right here. So we see that these two terms gets cancelled. The expression that we have is minus 90 degree of tan inverse of 1 plus tan inverse of R1 C1 divided by R2 C2. So what we see here, if in this expression, this takes the form of C1 by C2 root 2 plus root 2, that is C1 over C2 divided by 2. If we assume that C1 R1 is R2 C2, that's the ratio, right, is equal to 1. And if this is also equal to 1, so in this case, for the phase, we see that the final phase would be minus tan in 90 minus of tan inverse of 1 plus tan inverse of 1. So finally, it takes the value of 45 plus 45. So it is again minus 180 degree. Same as before, right here. So if we have this assumption, or if we make this factor to be equal to 1, finally, for the case, that was the case 3 right here. This is the case 3. What about the final case? We assume that omega is very, very greater than omega C1 and omega C2, or better be right, omega is equal to infinity. In this case, the gain will take the form of this value. So it would be in the numerator, we have infinity, and the denominator, we have this one, 1 plus infinity square. This is also 1 plus infinity square. What we have is infinity. This is infinity square, square root of, this is infinity square. So this is what we have. Square, it is 1 over infinity, and that finally goes to 0. And the angle would be minus 90 degree of minus of tan inverse of infinity plus tan inverse of infinity right here. So that takes the form of minus 90 degree minus of tan inverse infinity is 90 degree plus 90 degree. So this is minus 90 plus minus 180, that is minus 270 degree. So that's case number 4. Okay, we can also analyze the circuit at omega C1 is equal to omega C2. This is when the frequency is, these two frequencies are equal, these two pole frequencies are equal, and our signal frequency is equal to them. So in that case, again, the magnitude can be obtained, and we see that what value it will take. So how about we simulate this circuitry? So let's finally write this out. The final expression in this case, for this case, would be omega times, let's call it as a, let's write in this way. The final case would be omega is equal to omega C1 is equal to omega C2, and that is equal to omega C. Okay, so in that case, we have this gain omega C R2 C1 divided by 1 plus omega C over omega C, because omega C2 is now omega C square, and here 1 plus omega C over omega C whole square. We see here what value we have. So it is square root 2, square root 2. And that is omega C R2 C1 divided by 2. That's the magnitude we have. Okay, and what is the value of, this is R2 C1, R2 C1, R2 C2 actually. It depends what gain we set here. And the angle would be minus 90 degree minus of tan inverse of 1 plus tan inverse of 1 right here. Okay, so that finally comes takes the form of minus 180 degree. So when these two frequencies are equal and we assign it is the value of nu degree. Let's draw the plot, how it looks like and see. So that's our magnitude gain is 0. Here, let's say omega C1, let's say omega C2, is omega is infinity. Similarly, for the phase, we see this is your phi and this is your phi. So at the case number 1, at omega is equal to 0, we have magnitude 0 and the phase is minus 90. So let's plot that out. Magnitude is 0 and the phase is minus 90 degrees. Let's say like this. So when omega approaches omega C1 right here, the magnitude takes this form. This is the value, okay? This is the value actually. And if we make such arrangement so that the ratio of the two resistors is equal to the ratio of the two capacitors actually, and that is equal, that is made equal to 1, then we have this value. But right now we'll just write this magnitude R2 over R1 divided by root 2. So let's say this is R2 over R1 divided by root 2. And again, we have another factor here. So what is that factor? Right here, square root of R2 over R1 into C2 over C1. So let's write in this way. We call it A, and the value of A is R1 square root of 2 into 1 plus R2 over R1 C2 over C1. That's the value. What about the phase at these frequencies? The phase is varying. We see here it is minus 90 degree in this case, and the phase is minus 180 degree. If we assume that this is the case for the case 2, minus 180 degree. And otherwise, the phase is the phase varies as a function of these two values right here. R2 and C2, that's the product, divided by the product of R1 and C1. So it depends on what value we choose, the phase will vary. But of course, it is less than minus 90. So it's less than minus 135 actually. Okay, so it is going like that. So let's draw that. It is going like this. So it is minus 180 if we have about minus 180. If R2 over R1 equal to C2 over C1 is equal to 1 right here. Okay, so we have this magnitude right here. What about the next case? That is omega is equal to omega C2. Again, we have this magnitude right here. And if we have such arrangement, then we take the value of this one, C1 over C2 divided by 2. So we can write this too right here. So we have this at omega C2, we have another gain right here. So the gain is constant right here. And this, let's say this is point A, this is point B. This is point A, this is point B. And the B is, let's see what the value of B is. C1 over C2 divided by root 2. C1 over C2 divided by root 2 into square root of 1 plus R1 C1 divided by R2 C2. So we see that this is how it takes the value, right? And this simplifies to C1 over C2 divided by 2 if R1 C1 R2 C2 is made equal to 1. Is made equal to 1 right here. What about the phase in this case? The phase here, we are seeing that is approaching minus 180 degree again. It's going to be the same, right? If this ratio is equal to, if this factor is made is equal to 1. Because, and we've seen that phase is also minus 180. If we see that R2C1 into R1C2 is equal to 1. This is R2 divided by square root of 2. R2 over R1 divided by 2 if R2C2 R1C1 is equal to made equal to 1. And this is also this one. So the phase is minus 180 degree. For this also, the phase will remain constant. Is about 180 degree, minus 180 degree. If we see that we'll write in this way. This is the phase is 180 degree. And now, yeah, so if R2C2, R1C1 is equal to 1, or it's not and, it's or R1C1, R2C2 is equal to 1. So this is one case, this is second case. So that's how the phase goes like this. Let's draw it in the proper way. So that's how the phase is minus 180. What about the third condition right here? At omega is equal to infinity, or when omega is very, very greater than these two pole frequencies. So the magnitude is 0 and the phase is minus 270. So the magnitude is 0 as we go on, and the phase is minus 270, somewhere here, right here. Okay, so we see that this is the bandpass response for this. So these two frequencies, we have this constant gain, that is the values right here. The gain is available, and at omega c1 and at omega c2, the gain falls to the minus 3 dB value from the DC gain, from the gain which is constant. So it is minus 3 dB points. So it depends on what values we choose for these. Let's draw it in a proper way. Like this. So at these two frequencies, we see that these are the minus 3 dB points. Minus 3 dB points. And that's the gain, original gain. Okay, what about we try to simulate the response and we see that what values and what is the overall phase shift. So theoretically, the overall phase shift is from minus 90 to minus 270. We'll see that, for instance, we can actually also see one more response when the frequencies are identical. For instance, if we take a look at this, what about this one, final expression, when omega c1 and omega c2 are equal to omega, right? These two frequencies are equal, and we see that they have a constant value of this frequency. Then the gain takes this one value, this magnitude, and your phase is minus 180 degrees. So that can also be reflected, depends on the case. So let's now take a look at the simulation. We have this circuitry right over here. What we see here, we have an AC voltage source to analyze the frequency response, the value of which is set to 1. And we have a capacitor of 1 microfarad and 5 kilo ohm resistor in series. And we have this in the feedback resistor and capacitor. This is the load as usual, which is combination of resistor RL and CL, which is a typical load offered by an oscilloscope. Let's simulate the response of this circuit, and we see that here is the output. We have this bandpass response right here, and the phase shift from the right side. We see that we start from this point. We see that the phase total phase shift is from minus 90 to minus 270. In the theoretical analysis, can we see that if we have obtained, yes, the phase is varying from minus 90 actually to 270 right here. The phase shift would be like this. So we see this is how it's varying, and at the two frequencies are here. We'll see that what the phase is like. So at the center frequencies, the maximum gain that we have is about 0 dB. We can have that. So let's set the value of resistor to be, let's say 10 kilo ohm. We simulate the response. So we now see that the maximum gain that we have is about 4.35 or 4.5, about 4.43 right here. And in that case, the phase is minus 180 degree right here. And the pole frequencies at omega C1 is about 1.46, so minus 3 dB less. So it is about 23 hertz, and the second pole frequency would be at about 200 hertz right over here. And in that case, we have these phase shifts. So total phase shift is matching with what we calculated in the theory. So let's now take a look at what if we make these values equal. For instance, this R2C2 is made equal to R1C1. So we'll see that what the response looks like. For instance, we have this 10K. So 0.1, we have this 0.1. We also make this resistor to be 10 kilo. And now we try to simulate the response. We see here the gain, maximum gain that we have is about minus 6 dB. And the two pole frequencies at that point would be the phase shift is about minus 180 degree, and the two pole frequencies, we see that minus 9 is about 63 hertz here, and another is about 380 hertz. So it depends on what values we choose. We have this response looking like. Okay.